Okay, look at number 2 here. We've got a can that is to be made to hold 1,000 cubic centimeters of oil. And, if we were to draw a real quick picture, I think you can see that we've got a cylinder. And as soon as you read 1,000 cubic centimeters from your days in geometry, I hope you're going to realize that that's what type of a measurement. It's volume, isn't it? Now, last chapter, we were reminding you want to know the volume of a cylinder. What's that formula? It's pi r squared times h, right? And you could say, well, of course, we've got our r right here. We've got our h right here. By the way, those are the dimensions of the can, the radius and the height. If I tell you what the radius and the height of a can are, you're going to know exactly how big it is. And they're telling you something maybe a little obscure right now. They're saying, okay, it's 1,000. Very similar to the last problem where you were told the perimeter of your fence, and yet you were trying to talk about area. In this problem, they start you off and they'll say, look, this is the volume. So it's like a company is saying, look, we're going to sell cans of oil, and we want to make sure we're selling 1,000 cubic centimeters of oil, but we want to be smart. We're going to be making thousands and thousands and thousands of these cans. We want to minimize the cost of every can. Now, if you're going to minimize the cost, what on earth do you think we're really going to minimize? Not the volume per se. The volume has to be 1,000. The surface area. The surface area will be the material that's going to be needed. So if we were to look at surface area, guys, of this shape, I'm sure you can agree there's a top. It's a circle. There's a bottom. Every can's going to have a circle on the top, a circle on the bottom. By the way, this is pi r squared, and this is pi r squared. And then you've got the lateral, the smooth edge around. What kind of a shape is that? It's a rectangle. If you cut a soup label, and if you unfold that soup label, you'll get a rectangle, won't you? If you take a paper towel roll, and if you unwrap, much the same way like the label, you get a shape that looks just like this. And of course, you could say, well, that's your height. What about this length right here, the base of the rectangle? It's the circumference of the circle, isn't it? You guys have seen that before. And the circumference of the circle is 2 pi r. Now, they're not telling us a specific cost per square centimeter. They're not saying that this is like $3 per square centimeter or 3 cents per square centimeter, whatever it might be. But regardless of how much a square centimeter of metal is going to cost to create this, at the end of the day, you've got 2 circles. That's 2 pi r squared. You also have this lateral area, 2 pi r h, base times height. What's that? The C is standing for the cost. It's really the surface area, of course, but the surface area, you're going to multiply it by the cost of the metal. How much, you'll say, oh, there's so many square centimeters. And then you'll say, you know what, we have to pay this much money for each square centimeter of tin or whatever it is. So C is really the cost. In the future, you're going to have a homework problem where they're going to say, oh, the circles, the top and the bottom, cost this much per square centimeter. So, let's just say it was 3 cents. You'd go 0.03 times that. And the lateral area is less expensive. It's like 0.02, 2 cents per square centimeter. You could multiply that by 0.02. Here it's much more abstract. They don't even mention a cost at all. Okay? But here we go again. You look at this and you think, oh man, you got to be kidding me. I've got too many variables. If I'm going to take derivatives, I'm going to need to use the product rule. And oh my gosh, this is going to get all messy. Like I said, if that's the only thing you see right here, C equals and so on, it's become a multivariable optimization problem. You'd have to take derivatives with multiple variables. But is there another way to get some help? Well, I hope you can look at this and say, well, wow, what did we do in our last problem? In our last problem, we made a substitution, didn't we? We made a clever substitution. What substitution do you think we can do here? Solve for h. And you could say, well, I'm going to plug that in right in here. We'll say here's 2 pi r, but your h. Now this is where it can get a little scary for kids. Sometimes they look at that and they'll go, oh no, this looks really bad. You know, we went from something messy with, multiple variables. But now you look right here and you think, oh no, I don't know if this is so friendly after all. Actually, good things are about to happen. The pi's cancel. An r cancels down below, so you'd get 2 times 1,000 is actually 2,000. And then you'd have an r underneath. And yeah, you probably don't like seeing that r down below. But I'll tell you the truth. You can take a derivative now, and you can make it work out. Let's look at that r in the bottom as if it was r to the negative 1, just like so. So I can look at a function now and take its derivative. C prime. Taking a derivative with respect to r, what do we get? Well, 4 pi r plus, or maybe you want to make it a minus. You bring that negative down. You get r to the negative 2. And it doesn't take too long for kids to say, no, wait a minute. This isn't looking nearly as nice as our last problem. Nobody would deny that. They'll say, oh my gosh, look. Got this ugly fraction down below. And you might want to, even set this equal to 0. Simultaneously, tell you what, I'm going to try to get a common denominator. You might remember us doing that. Because when you're checking out derivatives, you're interested in where your derivative is 0 or where your derivative is undefined. And guys, that right there is your derivative with a numerator and a denominator expressed. Now, you look down below and you've got a critical number, that r squared. You could say, couldn't that equal 0? Well, you could, but imagine how silly you'd feel walking into your boss's office saying this, hey, I've got a fantastic idea. You want to minimize the cost? How about we make a can with a 0 radius? And he'd say, are you out of your mind? We want to build a can, right? Sure, save the most money by don't building a can at all. No, we're going to build a can, right? We're going to do this. So you go, okay, so then what? Well, you're going to actually be looking at where the top could equal 0. And this might not be the nicest looking equation that you'd ever see. You can divide both sides by 4 pi, and of course 2,000 divides by 4, and you'd even get, 500. And it's 500 over pi, and you can, write that out if you'd like. That would definitely be okay. But I guess what I'm really getting at is, at the end of the day, even if you didn't simplify it, if you wanted to get an answer with your calculator real quickly. And that's a good thing to do. We can say, well, let's get that cube root on. And we'll say math. Cube root's number 4. And then I'm going to say bring up a fraction. And whether you want to go 500 over pi, or if you didn't even catch that it could simplify, I know you did though. Hopefully you did. It wouldn't take you too long to say, hey, there's my radius. Right? There's my radius. It's about 5.419. Now, by the way, it might be a good idea to hit store and then do alpha r. You could even store it in for alpha x. But just in case you need to plug that in somewhere, you don't want to plug in just a few decimals. You want to make sure you're not rounding until it's at the very end for another measurement. So rest assured we've got r is about 5.419. Here's the big question. Do I know that that radius will minimize the cost and minimize our surface area here? Actually, we don't. We actually don't. So here's the tough question then. We can say, well, what do we need to do? Well, I'll tell you what, you could set up a number line. And you could check and confirm that you would get a minimum cost. But look, I do want to point something out to you. That's the first derivative test. I'd like to point out the second derivative test. The second derivative test is one of those ideas that kids can tend to forget. Sometimes they want to forget it. But look, if I took the next derivative, you can see I'm right next to it. C double prime would be, what's that? 4 pi plus 4,000, because negative 2 times negative 2,000. And here's r to the negative third. The second derivative test is not saying take the second derivative, set it equal to 0. It says find out where your first derivative was 0 and plug it in. Plug it in right here. So that's why I even stored it. You know, I could write out 4 pi, and of course right here it doesn't matter as much. I could have even used the answer button instead of storing it. But I could say, look, if I want to find out what my second derivative is, when I have 4 pi plus 4,000 r to the negative third, you can see very fast you get something positive, 37.699. So we're concave up for our cost function, aren't we? We're concave up. But I also, at this value of r, have a horizontal tangent line, because that's where my derivative was 0. If you're concave up on the parent function of the cost function, you're concave up there and you have, look at this picture right here. What kind of an extrema do you have? It's a relative minimum. So we can say we have a relative minimum at r equals 5.419 because our prime of, let's see here, I'm so sorry, right here, C prime of 5.419 is equal to 0, and C double prime of 5.419 was positive. Okay? So I know there's a minimum, but they're also going to ask for what your height is. Your height is right over here. Height is 1,000 all over pi r squared. So get that calculator out, hit alpha y equals, and type in 1,000 all over pi r squared. And then you get your height. Your height's 10.839. Those are the dimensions that will minimize your cost. Your R was 5.419, your height's 10.8.